All right, class, welcome to Math 2020 video for section 3.3 of the angles of a polygon. So a polygon, to review, is a two-dimensional geometric figure that is enclosed by straight lines segments. And so polygons have sides and angles. So we're going to study the interior angles and exterior angles of a polygon. First, we're going to think about naming polygons. In this example, we have a table that we will fill out that has the name of the polygon, number of triangles, and the sum of the interior angles, however many angles inside it. And all of it is based off of the number of sides that it has. So right here we're going to put in number of sides. Okay, so if a polygon has 3 sides, you all know it's a triangle. Let me zoom in here. There we go. Okay, so for the first part of this video, we're going to focus on just naming the polygons. Okay, polygons are named from Greek prefixes based off of the numbers of sides. Okay, with one exception, that's number 4. Okay, so number 4, the Greek prefix is tetra, but the polygons that we are named, as we know already, that have 4 sides are called quadrilaterals, and use the prefix of quad, which is Latin. Okay, so if a polygon has 4 sides, it's a quadrilateral. 3 sides is a triangle. But from now on, naming polygons, we use Greek prefixes because the Greeks were the culture that spent the most time on the geometry that we have adopted in our geometry in the United States. 5. Remember, Latin prefix for 5 is quint, like in quintuplets. But Greek prefix is penta, as in pentagon. 6. The Latin prefix is sexta, like sextuplets. But with Greek prefix, we use the word hexa. So 6 is in hexagon. Number 7, if you have a figure that has 7 sides, polygon that has 7 sides, the Greek prefix is hepta. Many people think that this could be a septagon, but septa is the Latin prefix, like as in September or septuplets. Okay, Latin for 7, but we use Greek for 7, so we use hepta. Number 8, octagon. Number 9, nonagon. Number 10, decagon. 12, dodecagon. 20, icosagon. And n is going to be any number of sides, so we usually call that the n-gon. Okay. Any number of sides. Now what we're doing in this table is that we're also thinking about the number of triangles. And what the number of triangles will do is that will help us find the sum of the interior angles. Okay. And that's our goal, is to find the sum of the interior angles of any polygon. What are all of those angles added together? And we have some example polygons down here, and interior angles means these ones right here. So inside the triangle, we have these angles here. I'm marking them with one mark, and we know that the triangle has one triangle in it, and the sum of the interior angles is 180 degrees. We've proved that before in the past with cutting off the angles, setting them next to each other, and seeing that they add up to 180 degrees. Now in a quadrilateral, here's an example of a quadrilateral down here on number 2. We have 4 angles here. In a quadrilateral, we want to see how many triangles we can make. And we can make any number of triangles in any figure, because you just draw on like some right here and just keep dividing into triangles. Okay. But what we want to do is define the sum of the interior angles. We're going to divide each figure that are given, these polygons in this for the second column here, into the minimum number of triangles. So that what's the smallest amount of triangles you can use? Okay. And with any quadrilateral, we can divide it into 2 triangles. And the sum of the interior angles of these 2 triangles, we have 3 angles here and 3 angles here. Okay, and because there's 2 triangles, and we know that the sum of the interior angles of a triangle are 180 with 2 triangles, then with 1 triangle, then with 2 triangles, we have twice that much amount of space. Okay, I've illustrated it here with triangle number 1 and triangle number 2. And so when you add 180 and 180, you get 360. Okay. Now we're going to go to a pentagon. Okay. And for a pentagon, I'll draw one right here. So you can see 5-sided figure. And how many angles do we have in it? Okay, how many triangles can we make? From this vertex, I'm going to draw out 2 lines, triangle 1, triangle 2, triangle 3. Each of those triangles has 180 degrees in it. So there's 3 triangles, and I'm going to calculate it by doing 3 times 180 degrees. And when I do that, I get 540 degrees. So the sum of the interior angles of a pentagon, which I'm going to highlight in red, are all equal to 540 degrees when you add them up. Okay. Hexagon is a 6-sided figure. We have an example of a hexagon down here, number 2. I'm going to draw out the minimum number of triangles, which is 3, and the sum of those angles right here. Oh, I make a mistake. There's 4 of these in here. So I have 4 triangles. I'm outlining all of the angles in each of the triangles. Okay. And so when we add them all up, we'll get the same amount as 4 triangles. So we're going to go with 4 times 180 degrees. There are 4 number triangles inside that pentagon there. Triangle 1, triangle 2, triangle 3, triangle 4. And when I get 4 times 180, I get 720 degrees. Heptagon. Well, do we want to keep drawing figures? No, that's what the power of mathematics is for. Notice that the number of triangles increases by 1 as the number of sides increases by 1 in the second column. So a heptagon has 7 sides. Therefore, we must be able to fit 5 triangles inside there. 5 times 180 is going to be equal to 900. And so on. Octagon has 6 triangles can fit in there, has 8 sides. 6 times 180 is equal to 1080, 1080 degrees. In a nonagon, you can fit 7 triangles. 7 times 180 is equal to 1260. In a decagon, you can fit 8 triangles. 8 times 180 is equal to 1440. Excuse me. In the dodecagon, you can fit 10 triangles. 10 times 180 is equal to 1800. Icosagon, you can fit 20, no, not 20. Let's see. The difference between the number of sides and the number of triangles is 2. So the icosagon can fit 18 triangles, and 18 times 180 is equal to 3,240. So all of the angles in an icosagon add up to 3,240 degrees. If you put them all together, then it would be more than circles. Now the n-gon, we have n number of sides, so you can fit n subtract 2 triangles within them, according to our pattern. And to know the sum of the interior angles of any polygon, we just take the number of sides, subtract 2, and then multiply by 180. Okay. Let's take a look at number 2. A regular polygon have all sides the same length and all angles are equal. Okay. Which of the following are regular? Well, let's take a look at this first one, this first triangle here. It looks like it's isosceles because these two sides are the same. And this one is not the same. So the third side is not the same as the other two sides, which means that only the base angles are the same. The base angles equal each other, but no other angles. So that means that it violates the angles at least, angle measures and the side measures. Okay, so this one is not a regular polygon. This rhombus is also not a regular polygon because this angle here and this angle here, even though they're the same, but they're not the same as these angles here, even though they have all the same side lengths. So it satisfies the first requirement, but not the second. This right here is an equilateral triangle. All of the sides and all the angles are the same. All the sides are the same, all the angles are the same. This is regular. Put some clues down here. And this is the equilateral triangle. This right here is a hexagon. It is also regular because all the sides are the same length and all the angles are the same measure. Now, if we're going to find the sum of the interior angles of a polygon, just like we reviewed before, we have a vertex method. You can find them by breaking the triangles from one vertex. So I'm going to pick this vertex and draw triangles in it from one vertex to another. Sorry about that. Okay. Okay. And we can do 4 triangles. Triangle 1, triangle 2, triangle 3, triangle 4. Okay. And when you break them up into triangles from one vertex, you can count the number of triangles and then multiply that by 180 to find the interior, some of the interior angles. So with this one, we have actually a group of, we have 4 groups of 180 degree sets of angles. Now, we can also use a point method to find the sum of the interior angles. So put a point in the center and then break it into triangles. Putting a point in the center here, break it into triangles, which I'm connecting to the vertex of each one. Now, in this figure, we have 1, 2, 3, 4, 5, 6. We have 6 sides, so it's a hexagon. Okay. And the interior angles of each triangle angles is equal to 6 times 180 degrees. Okay. And so what I've done is I want to make sure that I'm counting just the outside angles here of the interior angle, sorry, the inside of the angle of the figure. And there's some angles that are being double counted when I do 6 times 180. Because we know that 6 times 180, according to our thing, oops, is 1080. But our hexagon, according to our thing, our table, says that it is 720. So it looks like I'm double counting something. Because my answer is too high. So I'm going to subtract off this part right here in the middle. I've overcounted these angles here. So I'm going to have to subtract off 360 degrees to compensate. And that will give me my 720. Okay, for number 5, what if the polygon is concave? How can we break the polygon into triangles? And how the number of triangles relate to the number of sides? Alright, so concave polygons, just so you can remember, are polygons that have angles that go inside the figure. Okay, or if you draw 2 points in the figure, they will cross outside the figure. That's the definition of a concave polygon. The convex polygons are the ones that we are normally working with, like the octagon down in number 7. So if we want to find the sum of the interior angles, okay, here's the interior angles for this polygon. We have one here, one here, one here. Notice that the reflex angle. One here, one here, one here, and then another reflex angle. Those are the angles of the polygon. How many sides do we have? We have 1, 2, 3, 4, 5, 6, 7. So it looks like we have an irregular heptagon. Okay. Irregular, which means all the sides and angles are not all the same. This is convex, and it's a heptagon. That's about our figure. Now we want to do, if we draw the method to separate these into triangles, will it work the same as with convex polygons? So I have a point at one of my vertices. I'm going to connect it to all the triangles that I have here. And at this point right here, to connect it up to that outside corner, outside vertex, we have to go outside the figure. So we're having like triangles or parts of triangles that are not configured correctly for our formula, our property. So let's try the point method on the inside. Maybe this will help us. I'm going to draw a point here, connect it to all of the vertices. Okay, so that one doesn't quite look good, so maybe let's try and go a little bit out this way. And get that triangle right there. There we go. Because this method should work if I draw it all carefully. Okay, so we have 7 sides. Let's see how many triangles there are. If I do the point method, it should be the same amount. So it's triangle 1, triangle 2, triangle 3, triangle 4, triangle 5, triangle 6, and here's triangle 7. So I have 7 triangles, which is good. 7 times 180 degrees was equal to 1260. Now what I did was I overcounted because I went with the point method. So I had this one right here, this one right here, this one right here, and all of these angles around here are double counting, are being overcounted here. So I'm going to have to subtract off my 360 from my inner circle there, and I get 900 degrees, which checks out from our table. So it looks like that concave polygons do not matter. The interior angles are, even though some are reflex, are still the same. Number 6 is some of the exterior angles of a polygon. First of all, what is an exterior angle? Let's try and draw one up here. Use blue. Exterior angle of a polygon. And what we have with our exterior angle is that, let's just draw a polygon, like quadrilateral maybe. Here we got like some sort of trapezoid. Okay, and I'm going to extend the base, and that's the exterior angle this way. Okay, so any base you extend and then you choose the outside of that figure, that's your exterior angle. But the racetrack method of discovering the sum of the measures of the exterior angles goes like this. So I'm going to draw a figure, a random polygon. Okay, this is a random pentagon. Extend the bases. And then I want to find the measures of this angle, this angle, this angle, this angle, and that angle. All of the exterior ones. So racetrack method takes a car. So let's draw us a purple car along a track here. So I'm going to start right here and do rectangle for our car. And our car is going to zoom along in this direction, and it's going to turn this direction. Now how much it turned is indicated by this red arrow. It was on this side and it turned that way. Okay. And our car is going to continue going on. So I'm going to show all the terms here. There's our purple car. Oh. Okay, and then it drives up here. It goes this way. It drives back and turns that way. Drives this way and turns up this way. Now, from start to finish, how many degrees did the car turn? Well, if it starts in a certain spot, does a bunch of turns, and then ends up in the same spot, then that means it has turned one complete revolution. Okay. So the racetrack method shows that the sum of the exterior angles of a polygon are is equal to 360 degrees because I started at one spot, made a bunch of turns, and ended up in the same direction, same spot. Now zoom out method you could see this a little bit. Zoom out method. So we'll start with our generic polygon. I'm going to extend the bases again. Okay, these are going to be, and not just line segments, but there'll be arrows here. These will go on forever. Okay. So zooming out, so zooming in, zooming out. Okay, so that's the zoom out method. But let's go ahead and draw a depiction of the zoom out method. So just instead of doing zooming in and out, if I were to zoom out on this figure, the figure itself would go really small. So I'm going to draw the figure again in a smaller size because I'm zooming out, making this figure small. Extending the bases. Oops. To keep it the same as the other one. Okay, so notice that that's getting smaller. We're going to do all the way till that figure becomes a pinprick. And the pinprick will be just like a dot, but in the direction and the amount of arrows will be the same. Okay, so that one corresponds with that one. This one will come out like this one. This one will come out like this one. This one will come down again. This will come left again. So notice that it has become a point, and all of the angles around this point, as we know, are equal to 360. So it becomes angles at a point equals 360. Okay. The base point method we won't do here. So I'm going to draw over that one. No base point method. You could read about it in your book if you'd like. Now we're going to find the measure and do some practice here. What is the measure of each interior angle and exterior angle? Oh, interior angle of a regular polygon. Okay. So if we wanted to find the interior angles, all interior angles together, we'll start with that, and then we will go to each one. So all interior angles, the formula is n minus 2 times 180. So for an octagon was 8 minus 2 times 180. Six times 180. And we get that one to be, again, just from, which is 1080. You could even look that up on your picture. Now, if all the interior angles are 1080, this is a regular octagon because all the sides and all the angles are the same. We can take the 1080 and divide it by 8 to get the measure of one of the angles. One interior angle. Okay. So the 1080 divided by 8 we get is 135. Okay. So let's measure the interior angles. This angle right here, for example, is 135 degrees. Angle alpha, or we'll just call it angle A for short. Angle A is an exterior angle. So we know that all exterior angles are equal to 360 degrees. one exterior angle, take our 360 degrees, divided by 8 to get one exterior angle. Now 360 divided by 8 is going to be so do it on your calculator. .45 degrees. Okay. So this is equal to 45 degrees. Okay, so that's our lesson on angles in the polygon. In the homework, you'll have, this is going to be your key equation. Okay, so we'll circle that in green here. N minus 2 times 180 equals the sum of all of the interior angles of a polygon, all of them. So sometimes you'll get the number of sides, and you have to find the number of angles, the sum of the interior angles, but sometimes you'll get the sum of the interior angles. Okay. Okay, what happens if and then sometimes they'll give you this, and you need to find out the number of sides. So the sum of all interior angles is equal to something. You set it equal to this formula, n minus 2 times 180, and then solve it for n. Okay, so there's a clue on some homework problems.